So I'm going to talk a few minutes today about the Wyoming Technology Business Center and what we do. And then I'm going to introduce a panel of technology-based companies that have an energy focus and let you see different types of entrepreneurs and how they've started their businesses. And I'll provide some more detail on that later, right before I'm done. So the Wyoming Technology Business Center is a business development program at the University of Wyoming. Our mission is to support the startup and growth of early-stage technology-based and entrepreneurial businesses, and to encourage the development of an entrepreneurial ecosystem in the state of Wyoming. Our primary program in doing that is a business incubator. And so the idea of a business incubator is that you combine space with access to shared services and business and management advice for early stage businesses. The thing that makes a business incubator an incubator instead of an office building is that hopefully you do something that supports the growth and development. And our goal is to help companies grow larger and faster than they would otherwise. And it is through a business and management advisory program. And just to give you a quick overview to that, we think of starting and developing an early stage program as in 4 different phases. The first phase is pre-venture. So when you're in pre-venture, you're thinking about getting into business. And when we have a client like that, we take them through a process by which they can assess their idea and what might need to be done and the appropriateness of that idea and what might need to be done in order to develop it. So they are in a position to decide, yes, I want to do this, or no, I don't want to do this. And the end of that is when they say yes and they incorporate a business. The next stage of development is pre-revenue. In pre-revenue, what you're doing is you're developing your product or service. Sometimes if it's a service business, that goes pretty fast. If it's a product business, sometimes it can take years. And you go through this process of developing a product, an experimental prototype, an alpha prototype, a beta prototype. In the beta prototype, you're working with a customer. Customers are actually testing your product. And what you hope is that those beta testers become your first clients. The end of this is when you have something to sell. And the next stage that you go through is initial sales. When you're at the beginning, you're not trying to penetrate a market. You're trying to get one customer. And then you're trying to get another customer. And then you're trying to get a third customer. And through trial and error, you figure it out. Nothing ever works the way you think it's going to work. You have to have experience, get that experience, trial and error, and you figure out a sustainable business model. Sometimes this takes months, sometimes this takes a while. And the end of this phase is when growth really picks up. And on the first 3, there's like a definite, first couple, there's a definite ending and starting point. And the next stage is first growth. And it's really different than the other stages because this is when you build an organization. Up until this time, and the kind of companies that we work with, the entrepreneur is the business. If you have people working for you, they're like staff. They're helping you with your job. And your job is the company. And when you get to first growth, you become overwhelmed. That's how you tell. The entrepreneur is totally overwhelmed. And what they have to realize is they cannot grow a business by working harder and harder. They have to work through other people. If they can't work through other people, they can't grow a business. And this is where we help them build an organization, and they start to hire people. They create a layer of middle management. They build structure that they didn't have before. And all stages are critical. But if you want to become a $3 to $5 million business, which is what our goal is when we start working with clients, you have to build an organization. It won't happen otherwise. Our clients go through a selection process. We really are targeting people and technologies that we believe you could build a $3 to $5 million business with a 10 to 20% net profit margin. The reason these are important companies in anybody's economy. They have a employment base that they pay benefits to. People get vacations. Everyone that works for that company sees how it's done, so you get spin-offs for this. So a $3 to $5 million business in an entrepreneurial area has benefits that exceed the amount of money that they pay in wages and the number of people that they hire. So we started in October of 2016. We have a 30,000 square foot facility. It's a mixture of office space and lab space. And when we opened our doors in October of 2016, we were full. I mean, that was really kind of exciting. It was also, pardon me? 2006, right. Thank you, Dave. It was really exciting, and it was lucky because I came in 2005, in July of 2005, when they started building the facility, and I started looking for clients. And I found a few clients, and we got temporary space on campus, and we started up the incubator, and I kept looking for more clients. And by the time we opened in October of 2006, we were full. And the implication of that is, whoa, there is a lot going on in Laramie, Wyoming. And then I go like 2 years and I hardly have a prospect. Well, I had started a technology incubator at the University of North Carolina at Charlotte in 1986. And ran that until 1998, and then I was CEO of a medical device company, and that's what I was doing when I came here. Well, in Charlotte, the more clients I got, And I came to realize that the entrepreneurial ecosystem in Laramie was not naturally spinning out these potential $3 to $5 million businesses. And unless we went further upstream and started working with people thinking about getting into business, we were not going to have a flow of clients. When I was in Charlotte, I never worked with a pre-venture company. I hardly ever worked with a pre-revenue company. I had a flow of clients that already had a product to sell, and we're beginning in that first sales stage. And why would you go further upstream if you don't have to? Because there's more risk involved. So we realized that we really had to become experts in dealing with pre-venture businesses. And we started an organization that we call E2E. It's a program of the Wyoming Technology Business Center. E2E is a networking educational group. It brings together entrepreneurs with people interested in entrepreneurship, helps us get to know each other, and then we talk about issues related to growing and starting a business. It's an hour and a half, 45 minutes of networking, 45 minutes of a program, and our program usually is we bring in a successful entrepreneur and they talk about their story. And these are not professional speakers. They tell their story, they tell you the good things and the bad things. And the message that we hope to get through with each of these presentations is to show the people in the audience, look, real people do these businesses. Maybe you could do a business. And if you're thinking like that, please come and see us. We meet 5 times a year, and we have chapters in Laramie, Sheridan, and Casper. Just to talk about some of the graduates, so our goal is to grow $3 to $5 million businesses. All of these companies achieved a $3 to $5 million business. Falcon Technologies was really the first one to exit. They were with us about a year and a half. They were in first growth when they came into the building. And so they were much further along in the process. They make specialty computers for stock traders. And they became an Inc. 500 company, one of the largest, fastest growing hardware companies in the United States at that time. Another company is Firehole Composites. This was a spin out from the university. They made a software that helps a manufacturer or developer of composite materials do a fault analysis. They grew, and then they sold to Autodesk, which is a big California company, and now Laramie has a division of Autodesk because of the acquisition of Firehole. 2 of our fastest and largest companies are Medicine Bow Technologies and Bright Agrotech. Both of them are still growing at a very fast rate. Bright Agrotech makes vertical hydroponic systems. So in a greenhouse, a typical hydroponic approach is a horizontal layer, and you're growing things in water. And this is like a gutter that goes up, and it allows there's things in there that hold the plant so that you use more of the cubic feet of the greenhouse. They grew fast. They have now 42 people that are working for them. Wyoming Business Council is going to build them a building that they're going to move into in a while. And they've really continued to grow and are now becoming profitable. Medicine Bow is probably our largest company. They do outsourced IT for rural hospitals. They were really started by Ivanson Memorial Hospital, which funded them, and they're now moving towards. So the idea is, it is a portfolio. I mean, you try to grow $3 to $5 million businesses. You do that because it stimulates other people to do businesses, and they also hire people, and they pay wages. They create stories. But out of that, you hope some of them can become $10 to $20 million businesses. And right now, as I look at it, I think Medicine Bow and Bright Agritech can become a $10 to $20 million business. So we have a statewide focus. We manage incubators in Laramie, Casper, and Sheridan. So we have full-time staff in each of those locations. The program, so what we're doing is scaling our business. And when you scale a business, what you do is you need to have a successful model. And then the challenge is you want to repeat that model someplace else. And so we start out in each of these locations with the same sort of approach to stimulating entrepreneurship that we do in Laramie, and then you change and adapt to the different situation. If it doesn't work, you change it, you try something else. It is true in all of these locations that the existing entrepreneurial ecosystem does not naturally spin out businesses at a very fast rate. So these are small cities and towns. The National Business Incubation Association used to say that in order to develop a successful incubator, you needed 75,000 people in a location. Well, we don't have anywhere near 75,000 people. And so you have to the focus has to be on really trying to stimulate people to think about starting a business, because naturally we won't have enough deal flow. We don't have deal flow. Okay, so the question then is, have you ever wanted to start a business? Now, if I'm in the Silicon Valley and I ask a random group of people that question, I'm going to get a different answer and a higher percentage of people who have thought about doing a business than I am if I'm in Laramie, Wyoming. And the reason for that is that if you're in the Silicon Valley, I mean, you have a house, neighbors on both sides have started businesses. Everybody knows somebody who started a business. It's real. They see it happen. And that causes them to think, gee, I wonder if I'm interested in doing something like this. And so what we try to do is do things that get people, to stimulate people thinking about getting into business. One of the things, if you come to me and you say, look, I really would like to start a business, but I don't have a good idea. So, and what we tell them is you don't need a good idea, you need to find a good problem. So there are two major types of businesses. One is you're a business and you're selling to an individual. That's called a business to consumer. You're selling, coats, hats, shoes, different types of retail products. The other kind of business is you're a business and you're selling to another business. And when you do that, a B2B company, and when you do that, you are solving a problem for that other business. You're helping them make money, you're helping them save money, you're helping them do something that they want to do but couldn't do otherwise. And the deal is that the more important that problem is to that business, and the more highly differentiated you are from the competition, the faster they buy and the more they pay. And in a startup, that's what you're looking for. So by saying, look, find a problem, I now suggest a process that you can follow. If it's looking for an idea, I don't know how you find an idea. I mean, it comes to you in the middle of the night or something like that. So we really focus on trying to get people to do business-to-business companies. Our philosophy in trying to stimulate businesses we use the E to E. This is really to try to stimulate people to do businesses. They come, they see real people do businesses. We publicize the success of local startups, and we offer counseling to people thinking about getting into business, to help them through that problem and solution. And in the last year, we have done some things with entrepreneurship competitions. So we raised $125. Our first initiation with entrepreneurship competitions was a $30K business plan competition that the College of Business runs at UW. And we started out and we gave the winner of that space in the incubator for a year, and then we started working with the different students that were doing a business, the finalists, And, I mean, we got some of our best companies from that. That's how we found Bright Agritech. And one of the things we wanted to do is to try to do that on a broader scale. And so we had there's a entrepreneur in Denver that gave us $100,000, and Mark Northam kicked in $25,000 so that we had a pot of money. And what we wanted to do was something that where there wouldn't be first, second, third place businesses. We wanted to create a fund. And the competition would be to qualify for the right to apply to that fund for money. And so we marketed it. They put their business idea, they give it to us through our website. We try to make it easy to apply. We sort through them. We choose the 10 to 15 that we think are the best. We bring them in for an interview, and then we choose the finalists. And we did this last year. We had 47 student teams that applied. Of the 47, 85% of them came from the College of Engineering. This is really different. And there were some really great ideas. We went back and we asked them the question, so how'd you get your idea for a business? And in 27% of the cases, they said, well, I heard about the competition, and I thought, what kind of business could I start? And in 47% of the cases, they said, well, I had this idea, but I hadn't really spent any time on it. So in almost over 70% of the cases, this competition caused these students to either come up with an idea or act on an idea. And so that's a really different thing for us. We talked to the semifinalists. We liked them all, so we made them all finalists. So we had 11 finalists. And we then worked with them from May to November, helping them put together a pitch. And then there was a judging in November. By the time of the judging, we had 8 of them left. 3 of them had dropped out. And of the 8, we qualified 6 of them. And if we qualified them, we gave them immediately $2,500 and then worked with them to come back and make an ask. So these are grants. They don't have to pay it back. But we treat it like an investment situation. So we want them to tell us, look, this is my business. This is how much money I want. This is how I would use the money, and this is the impact this money would have on our company. And all 6 of those finalists have incorporated businesses and are preparing to come to us to ask for money. So they'll get like $20-some thousand. It's not a lot of money. And the same is true. We did last year, we also did in the spring an entrepreneurship competition in Casper, and we did one in Sheridan. And this one was smaller. We raised money. In Casper, we got money for 2 years from the Albogan Foundation, from CATA, which is the Economic Development Group, and from the WIDC Frontier CDC. And it was the same process that we followed with the Fisher. We got the same results. In fact, we talked to the semifinalists before we talked to the semifinalists in Laramie. And it's really where I got the idea that people were coming up with an idea for the competition. And I didn't know that was happening. And what you find out is, and most of the time, people apply through this in the competition, and they do not have an idea that they are actively working on. The other thing, just real fast, and then I'm done, our basic marketing strategy in an area is through networking. We go out, we talk to businesses, anybody that we think an entrepreneur might go to ask advice from. Because if they're doing a business now, 6 months ago they weren't, and anything we were doing to try to get their attention 6 months ago, they weren't paying any attention to. And so we usually get 2/3 of our clients through referrals. And with a competition, it's like a step before that. When we get somebody through referral, they're already working on a business. In a competition, we are really stimulating people to take action, to either come up with ideas or work on ideas. Because of the success we had last year, we raised money to do a startup competition in Sheridan. We got money from CETA, Joint Powers Board, the Scott Foundation, First Interstate Bank, and Davis and Cannon. So Sheridan's a small place, 16,000 people. And we've been there about 2 years, and I got to tell you, we've had a hard time finding potential $3 to $5 $5 million businesses. And we did this competition. We marketed it. We had 68 people who applied, 68 people in Sheridan, the most we've had in any area. And of that, when we just did the choosing of the finalists last week, we got 10 semifinalists. And really, all of the 10 semifinalists had potential for $3 to $5 million businesses, and we chose 5. And I'm really excited about it because for us, it's a great marketing tool. And it allows us to find the kinds of companies that we're looking for to help develop in an area. So this panel is energy and entrepreneurship. We have 4 companies. All 4 of them are clients of the Wyoming Technology Business Center. Robert Lumley is going to be our first speaker. The entrepreneurs are different. Robert is a serial entrepreneur. He told me that he hasn't had a W-2 since 1991. And he started a business in the early 90s that was a business process outsourcing business, which included developing a large presence in India of software developers. And he did that from 1992 to 2003. And then he became a real estate investor and a developer, which he did in Hawaii from 2003 to 2007. And he started AirLoom in 2013. Dakota Robertson was one of the finalists for the Fisher competition. So he is a student. He's getting his PhD in electrical engineering. This is a business that he has developed and is now starting up. Casper Krukamelis is the CEO of Pollution Control Technologies. I did it really good before the panels thing started. He has a PhD in chemical engineering. We found him through the 30K competition. They've been in business almost 3 years now. Poya Nikoyan with Resono Pressure Systems is a PhD candidate in mechanical engineering, and he's doing a business that he is cooperating with his advisor on, and which he's using for his dissertation. If you look at capital, Robert started. I think you're going to see a group of different people starting companies, and you can see what motivates them and how they're doing. Robert had startup capital from himself. He bootstrapped it, and he had one investor. Dakota has had no investment yet. It will be their first investment in that business. He's also trying to get a Small Business Innovation Research Grant, which is a program in the federal government. They're grants, and you don't have to pay them back, and you own all the intellectual property. 2 stages. First stage, $150,000. Second stage, $750,000 to $1 million. Kaz has gotten an NSF grant. He got a phase 1, and now he's on his phase 2, and the phase 2 is like $1.2 million. And he's Poya also has not had any investment yet. Ours will be the first investment in his business. They're all in the stage of pre-revenue. And they have different technologies that are energy related. And so what I'm going to do is they're going to go in the order that I just went through, and we're going to have a presentation, and then when one is done, they'll be followed by the next. Please join me in welcoming Robert Lumley.
I'm always happy when it works.
Absolutely.
Hi. So I'm Robert Lumley, and I've developed a completely modular, completely scalable wind turbine, which would be utility scale, based upon an entirely new geometry, but using the same basic principles as a traditional wind turbine. And we moved to Laramie, Wyoming about 2 years ago, my wife and I, from the sunny spot of Kauai and then Santa Barbara. And we came here because there's a great purple spot of wind between Laramie, Cheyenne, and Wheatland. It's the windiest spot in the country. And I actually started off kiteboarding. Well, I've done a variety of things, but when you're kiteboarding, there's nothing worse than looking for wind. And when you're an entrepreneur, there would be nothing worse than paying engineers to be sitting around looking for wind. So we've been very happy with the wind here in Laramie. But actually, we've also been really excited about the incubator. It's been great for us, and I didn't expect that at all. Within 3 months of being here, I was the keynote presentation for Senator Enzi at his Inventors Conference. And for the first year, I was by myself, and it was great to be able to bounce ideas off the incubator. So actually, I would tell any entrepreneur to move to Wyoming because it's great. So now on to the AirLoom. So compared to the 3 blades of a wind turbine, we run multiple small airfoils on a rail. And it's the exact same aerodynamics, but we end up with shorter lever arms, and we end up with forces held by tension rather than compression. And as a result of that, it's a completely modular, completely scalable wind turbine that's 15 times cheaper than traditional wind turbines. I've been awarded 5 patents on it, and I've won an NSF grant to develop this technology, and it's actually really exciting. And we feel we're at the point of exponential growth, actually. So the first thing is it's so strange that I actually have to do an animation to show people how it works. So some of you have seen this before. Oh, it didn't come up. Sorry about that. Hold on, please. Technical difficulties.
Fred to the rescue.
Yeah. So let's get out of here. Hold on, Fred. I think I got it. Sorry about that. Now we have it. So here's a traditional wind turbine. It's on a football field for scale. And I don't know if you can see the football field up there, but it's very clear on my screen, I guarantee you. Here's a small wind turbine. The windsock shows you the direction of the wind. The wind is going across the football field. This wind turbine has a blade size of about 12 meters. It's got a capacity of about 100 kilowatts. The red tips are actually where the power is generated. They're generated there because, like a pizza, the outer tip is much bigger than the inner tip. A 12-inch pizza is much larger than a 10-inch pizza, and also those are going the fastest. Here's a larger wind turbine. This wind turbine has 25-meter blades. It's got a capacity of about 600 kilowatts. Still, just like the original one, most of the power is still generated at the tips. The rest of the structure is there just to support the tips. And the interesting thing is that these blade tips are going 40 meters per second, and these blade tips are also going 40 meters per second. It's an optical illusion that it's going slower. They're actually going faster. I mean, they're going the same speed. Here's a large wind turbine. This is sort of state-of-the-art land-based wind turbine, 2.5 megawatt wind turbine, blade length of 55 meters, tower height of 300 feet. The tips go up to 500 feet, which is the limit of what the FAA will let you do without special permitting and zoning and things like that. These blades are each 180 feet long. It's 3 tractor trailer lengths to transport them and to get them into the field. It's just a huge hassle for these things. So what I have is what I call the AirLoom. And I call it the AirLoom because it looks like a loom. It looks like a weaving station. So it's an airfoil, just like the wind turbine has airfoils that are moving perpendicular to the wind. It's the exact same aerodynamics. It's the exact same motion. It's an airfoil moving crosswind. We have one 6-meter blade instead of a 55-meter blade. The other thing I should say is that the power of a wind turbine is proportional to the swept area. If you want to make it bigger, you just have to have more swept area. For a traditional wind turbine, that's pi r squared. For me, it's length times height. So we can make it long and low, or we can make it tall and not wide. So what I put up this picture to show that it's the same basic aerodynamics. It's an airfoil traveling on a small rail. The downwind forces are held by compression. Let me get rid of the wind turbine. The wind turbine is just there for comparison. So here we see it's the exact same aerodynamics, But the thing is, we can scale it. It's completely modular, completely scalable. We can add more blades to it. We can make it, whoops. We can make it wider. We can make it taller, and we can make it wider and wider. So it's completely scalable based upon the same parts. So this is what I think is exponential. It's the ability to do exponential growth. So I think it's an extremely exciting technology. The other thing is that let me reset the view. Compared to a traditional wind turbine, we have 4 big advantages. The first is short lever arms. Our wingspans are 6 meters versus the wind turbine, which has a 55-meter wingspan. It's like a pencil. A short pencil is impossible to break. A long pencil is easy to break. So we don't need very much material to cover our swept area. That's the first. The second is that our forces are held by tension rather than compression. These are small ropes that are holding the downwind force. The third is a little bit more subtle, and let me pull up the wind turbine again. For this large wind turbine, the actual electricity is generated at the hub. While the blades are moving at 40 meters per second, at the hub in the center, it's only moving at 1 or 2 meters per second. It's sort of a function of a circle. The magnets are what actually generate the electricity. So the magnets at the hub are only moving at 1 meters per second. My magnets are moving at 40 meters per second, so my magnets are 40 times more efficient. The fourth is mass production. These things are incredibly simple to manufacture and stamp out. We think that we can just extrude them out of plastic or aluminum or whatever other materials. So it's an easy manufacturing process. And the fifth is transportation. We can transport this in a 20-foot container. We can transport it in a 40-foot container or a 53-foot tractor trailer. Actually, 2.5 megawatts would fit in a 53-foot tractor trailer, compared to the large wind turbine I showed earlier, which takes 3 tractor trailers for each blade. So if we add all that together, we end up with a device that's 23 times less massive. It's only 4% of the mass of a traditional wind turbine, and it is 15 times cheaper than a traditional wind turbine. So, hold on. So thanks for giving me the chance to do the live presentation. People always ask about crosswind issues, and yeah, I know. We've thought of the crosswind issues, the offset wind, and things like that, and all of that is accounted for in our mathematics. So, back to my. So here I reiterate the advantages. So on this screen, we can see the mock-up of the AirLoom, which is in the upper left-hand corner, a traditional wind turbine, and actually the first prototype that my wife and I built 2 years ago to prove that it would work. Once again, I reiterate the advantages, because when I make these claims, nobody believes them. It's incredible, but it is an exponential change. Short lever arms, forces held by tension, not compression. My generator magnets move 20 times faster, and mass production. The result is it's 23 times lighter, 15 times cheaper. It's completely modular. We can make a 100 kilowatt one, we can make a gigawatt one. It doesn't matter. It's all the same materials. We just stamp out more and more of them. Easy to manufacture, easy to transport. Like I said, we can be low and long for zoning issues. We heard earlier about people not wanting to build things near load centers because nobody wants to see a 500-foot tall wind turbine for 10 miles. We can make them 100 feet tall, we can make them 200 feet tall, we can install them near canyons in San Diego. So you can be low and long, or you can be tall where the wind is stronger. It's really an optimization problem. It's funny, for a wind turbine you have one variable, radius. For us we have 2, length and height. And adding 2 variables makes a big difference. Here's our team and who we are working with. We won a National Science Foundation grant in July of 2016 to build our first prototype, and we'll get to that in a minute. We've been supported by ANSYS, which is the premier engineering software, and we're in their incubator program, and in fact have been featured in their magazine this month, I think. And at the University of Wyoming, we work with the Wind Energy Research Center, and we work with the incubator. The team is myself. I have a BA from Williams College. I do not have an engineering iron ring. I tell people I'm a Wikigineer. I'm a Wikipedia engineer. So I've learned everything I needed to learn by going to Wikipedia. And I think I've gotten quite far. The NSF says that I'm doing okay. We have 3 engineers. And so can you 3 stand up? And those are not, we have Mukwon So, who is Dr. Mukwon So, who is a PhD graduate from the University of Wyoming in mathematics, who does our modeling. We have Olivia Lim, who is a mechanical engineer and energy engineer, and Blossom Ko, who does our operations and communications. And for aerodynamics, we have a part-time intern from the University of Utah called Josh Hamblin. And the other part of my team is my lawyers who spend all the money and have gotten us 5 patents. We also work, as I said, with Utah State University and with North Carolina State University for power electronics. Am I okay on time?
Yeah, another couple minutes.
Okay. The technology is nice, but it's the numbers that really matter. And here we try to compare the economics of an AirLoom with a traditional wind turbine. And I will tell you, whenever I show this slide to people, I always hear, you're too optimistic. Your numbers are too great. You should scale them back a little. But I've been working on this idea for 3 years, and nobody has ever shown me where my numbers are wrong, so I keep putting up my optimistic numbers. For a traditional wind farm, and I guess the mouse doesn't go there, but we can see the total development cost for a 100 megawatt traditional wind farm is $160 million. Basically, it's $1.60 per watt. To develop an heirloom farm, it's about 25 cents per watt. It's almost 7 times cheaper to develop an heirloom farm compared to a traditional wind farm. And then if we get to the levelized cost of energy, which is the most amazing number down at the bottom. For traditional wind turbines, the levelized cost of energy is 5 cents per kilowatt hour. We think we'll be at about 1.1 or 1.2 cents per kilowatt hour. So again, I think it's that exponential, synergistic adding together of all the factors that I went through earlier, the short lever arms, the less materials, the easier transportation. Of course, we're seeking funding because we think we have a very small team and we think we're ready to grow. But what I like best is what the NSF said about our proposal. They said that the heirloom proposal includes a plausible first-order estimate of the minimum forces and structures required for energy generation with this topology. What that means is I say my device is 15 times cheaper, and they say I'm probably right. That's an amazing statement. The sausage factory. So we have spent, and you can see Olivia and Mukwon in the pictures. We've spent the last 3 months actually trying to build this device out in a field about 6 miles from here. And we've been blessed with 75 mile per hour winds, which create their challenges. So here we are in the construction process. And I'm doing this because Jon Benson said, show people what the entrepreneurship is like. And you have lots of ugliness and things that go right and things that go wrong. But we are trying to build here we are in the middle of the snow because we had a February 28th deadline. We had dedicated people building 50-foot towers. Our device is actually 250 feet long, so this is an extremely large prototype. And here we are raising it with actually $30 winches from Harbor Freight by remote control, compared to traditional wind farms where you need, multi-million-dollar cranes out there for weeks and weeks and weeks. Here it is hung. It's not perfect, and that's that's what we are working on now. We're trying to improve our modeling and things like that, but we have built this 250-foot oval, 40 feet tall, with 2-meter wings about 6 miles from here, and we're beginning to get data off of it and prove that the device works. So that's where we are. Thank you very much.
Great.
All right, I'm Dakota Robertson. I suppose I had to start with an obligatory joke about engineering rings. Thank you, Marcus, for that. So he says that when you use some engineering jargon, a piece of it falls off. I don't have one on today. Whole thing fell off in a glove a couple weeks ago. So what I'm going to do is skip all the jargon I've got prepared on this deck of slides, because it's a fairly political audience, and I wasn't expecting that. So we're going to touch on some of those aspects I don't have in the slides. This is Aktzin Systems. My name is Dakota Robertson, PhD student in electrical engineering, just to refresh everybody's memory. So real quick, actually I want to skip to, I'm kind of improvising here, so bear with me, but I want to skip to one of the more political statements that I was prepared to make, and that is related to energy storage mandates. So the comment was made, I believe, by Jason that in the previous panel that that a lot of the energy storage technology is driven by mandates. Is that? Oh, it's not showing up. Sorry. Driven by mandates. So we've seen regulations here in the past 5-10 years related to energy storage mandates. And they tend to leave out hydro storage as a mandate. But one of the things we've seen is investment, fairly substantial investment in energy storage projects at the federal level, where companies actually are given tax credits or some sort of incentives to buy capital expense items. So some sort of energy storage device, take a battery, giant battery, lithium ion or otherwise, and plop it onto the system. And I use the word plop because it's inarticulate and sort of clunky, which is what they do. It's inarticulate and clunky. But they get their tax break for it, so it might be $10 million, it might be $30 million or more. And they let the system sit there in the sun and not do a whole lot. So I've had experience with Sandia National Laboratories for the last 4 years, dealing with systems, say in Albuquerque, New Mexico, in a 114-degree desert, where a giant battery equivalent to several thousand car batteries sits in the sun and wastes away. Now they got their tax, Public Utility New Mexico, PNM, got their tax break from it, but they got nothing else. They got very little in return. And that's because there's no accountability. So we see my real political argument here, is that there's very little accountability related to energy storage. It's a great idea in theory, but 12 cents a kilowatt hour doesn't sound that great when you run it through 2 inverters in a storage device. And so they just let it sit there. And so I've experienced with some of these systems where I think that we can do better. And so I take the engineer's approach to that. And so that's where I'm going to start. And keep that in the back of your mind when we go through these slides with a bit more technical jargon than I started with. So the problem itself, as Dr. Benson here described to us, kind of the entrepreneurial process, starts with a problem. So I'm solving a problem that I've described to you as being one that's motivated politically, but also technically. The technological problems here are kind of interesting. I'm going to cover those real briefly. High variability of renewable energy that everybody's familiar with complicates the integration of high penetrations of renewable energy. And the current control devices used in these systems are rudimentary. And so what we want to do is we want to look at these Ford Taurus, the 1998 Ford Taurus version of control, and we want to modernize it and make it an Alfa Romeo and make it something that really works well for these crazy expensive systems. And so the problem is this is renewable variability. Take this giant photovoltaic sprawling system here on the left, top left, sprawls out across a hillside in Italy, and then put a giant thunderhead in front of it in the afternoon. You see this substantial decrease in power output. So the blue curve there is the 24-hour curve of the power output from a variable generator like one of these solar farms. And you see gigantic fluctuations in active power output that the system particularly doesn't care for. The system wasn't designed for this. Transmission distribution systems are operating typically on orders of magnitude slower time constants. So it doesn't like this sort of variability. And the red curve there, the bell curve, is the ideal power output from a system like this. And so that's the problem. The symptoms of the problem are pretty obvious. Wear and tear on equipment that was designed in 1957 and has been outstanding as far as reliability is concerned starts to suffer from this variability. Take, for example, this big low-tap changing transformer, which costs anywhere between $50,000 and a couple million, $10 million for one of these things. Sometimes they're custom ordered, and they're gigantic and expensive, and they're changed out on the order of decades. So once every two decades, they change one of these things out, typically in a low usage or in a standard usage environment. Now they're changing them out an order of magnitude more frequently on subsystems where this variability problem is substantial. Take, for example, in Charlotte, North Carolina, right by the triangle that these guys were talking about earlier, there is Duke Energy has invested in a large battery system to try to combat this. And it's almost comical. And if there's anybody from Duke in the audience, I apologize, but not really, because they spent a ton of money on this thing, and they got all their tax credits. They took taxpayer money, and then they put it in a Connex and said, what do we do with this thing? And they're trying to combat the variability from a photovoltaic system they placed on top of a nail factory 2 miles away that caught on fire because the roof expanded and popped some wires apart, caught the whole building on fire. It's a very clunky approach to energy storage. And so Jason, I'm not sure if he's still here, but he touched on the expense of renewable energy or of energy storage, and nobody's going to argue that it's not an expensive technology. But with the appropriately placed control technology co-located with it, and as energy storage prices and renewable energy storage prices decrease, there will be a need, along with the responsible accountability by utilities to make sure that the things they purchase with taxpayer dollars are being implemented appropriately. That's the caveat. That we can make some great strides with this sort of control technology. Also, I think this one probably hits home more than anything at the Wyoming Infrastructure Authority meeting, that thermal generators are tasked with regulation that they weren't previously. So in the break that we had before the previous panel, I was talking to some people who were discussing thermal cycling. And so ramping up and down generators that typically weren't meant to ramp up and down. That combined cycle plant in Cheyenne is actually a good example, a counterexample to this, where it's actually designed to be ramped up and down on the order of 10 minutes. However, 10 minutes is still it's an order of magnitude or more higher than the time constants we see with variability due to clouds moving in a high wind environment. So there's still a lot of progress to be there. And the customer here is utilities and renewable asset owners, private stakeholders, things like that. And so those are current symptoms that we've seen particularly in these demonstration projects. There's about 50 of them, or last time I checked, about 50 of them in the country that are 50 kilowatts or bigger, but we're moving into an exponential growth sort of thing. I'm going to try and hammer these themes home if I can. Makes it look like I'm paying attention. So the future symptoms are that we're going to reach a limit in renewable energy that we can put onto the system. So as most of you know, there's a lot of inertia in rotating systems. So say in Jim Bridger, we got a 2 gigawatt rotating mass. And that provides a lot of things. It provides electricity, but more importantly to the system, it provides stability. That rotating mass is very difficult to slow down. So take a bicycle tire and spin it, and then try and grab onto it. The faster you spin it, the harder it is, and the more mass you attach to it, the harder it is to slow down. The same goes for large rotating mass in traditional generation, and we don't have that with renewable energy, hence the variability problem. So eventually we're going to reach a limit where the rotating mass in the system, which is absorbing this variability now, can no longer absorb that variability. And what you see is higher frequency deviations from standard 60 hertz to the point where FERC and NERC and everybody else who's breathing down your neck, they start to slap fines on you. And so there will be a limit reached for renewable penetration sooner than later. And this is actually coupled to, and I'm trying to remember, it was Jason also who said, like Germany, was selling or was paying people to buy their power. Texas, ERCOT system, they've done it on occasion too. This is very closely related to that situation. And so these energy storage mandates, which I prefaced this whole discussion with, we're just seeing things that aren't being used to their full potential. And that's my technical, or that's what I'm going to move into a bit more technical discussion of the way we like to control these. There's one guy I know in the crowd who's an expert in control. I don't know if there's any others, but if there are, forgive me for the elementary presentation of this material. But really what we're trying to do is take a system that exists and control it more intelligently. So we're going to take this simple block diagram with a proportional controller, which is, again, this is the 1998 Ford Taurus version of power system control, and we're going to rip it out and put in the Aktzin version of it, which is a Ferrari. And we're seeing, in a preliminary sense, a factor of 4, 12 dB for Jeff, a factor of 4 more performance than the state of the art, which is substantial. So say you have a reduction of variability by a factor of 4. That means when you buy an $11 million battery system and you plug it in, you get a factor of 4, roughly, more value out of that battery. Think of this as your capital expense is $10 or $11 million, and it has a finite lifetime of 10 years. And how you use it from year 0 to 1, or 0 to 10, is up to you. You can let it sit there and bake in the sun, or you can really crank it up with a really sophisticated controller. It doesn't matter, because it's going to die in 10 years, just like your car battery will die in 10 years. That's it, full stop. And so we would like, in the interim, to really make these things workhorses. And so I'm going to skip the dorky presentation of what we do and move on to my last slide here, which is, I've already covered half of it, so we'll talk about the opportunity. This is also a sophisticated, sort of nuanced political discussion about what the federal and local government role is in this. So we see a lot of regulatory interest from FERC and NERC and others in frequency regulation. So for those of you familiar with frequency regulation, you have automatic generation control systems that regulate automatically generators across the system who are connected to this control, typically substantial, very large generators and others for spinning reserve, to make sure that the frequency stays within an acceptable bound. Now, energy storage has a particularly interesting niche in that regime, because with a sophisticated control system, you can hook that AGC system up to every energy storage device in the market that wants to participate in the market. And what that does is, one, it creates dispatchability. So a renewable device co-located with an energy storage system isn't necessarily dispatchable in the way that a traditional generator is, unless you have full control over it, where you can commit a certain amount of energy at a certain time for a certain duration. So this helps alleviate that on the local scale, and also on the larger scale, the interconnected system scale, where you can have dispatchers who are willing to have unit commitment sorts of transactions with holders of battery storage. One, that reduces, or that increases the level of penetration we're able to achieve while retaining a stable system. And two, it squeezes additional value out of the energy storage devices. So now maybe instead of 12 cents a kilowatt hour, which is absurd unless you live on the island of Hawaii, I think Maui is, I don't know, you live there, it fluctuates between 9 and 15 or more cents a kilowatt hour. Unless you live there, that's a bit steep. So we're going to focus on trying to get that price down with a more sophisticated method of controlling these devices. So from my perspective, Aktzin Systems, new company, the idea was to solve this problem. The problem's been effectively solved. We're in the alpha testing stage, fairly deep into the alpha testing stage, submitting patent pending applications, things like that, and working toward potentially submitting an SBIR. But really, we'd like to get in with an interested utility. This is Wyoming Infrastructure Authority meeting, so I've got business cards if anybody's interested in letting me come and play with one of their storage systems if they've got one available. But that's where we're moving. We're moving toward the beta testing version of this, where we can go out, get a system in our hands, start to tweak it, see what we can do with the grid-connected system with our technology. And so with that, I'm going to leave it there.
Thank you.
Yeah.
Good morning, everybody. My name is Kasper Skrukramilis, and I'm a CEO of Pollution Control Technologies. I would like to switch gears here from a little bit from controlling energy storage to controlling, managing pollutants for coal-fired power plants. And our company is actually targeted at a very niche product. It's called XFA. X stands for halogen, and then FA is a fly ash, where we basically create this new material that basically controls the pollutants from the flue gas. Company was started 3 years ago. We've been extremely thankful to Jon Benson here in Wyoming Technology Business Center. We've been there for pretty much all our existence, and the operation of company, initially this was a research idea, over a conversation at the bar, and then we had a approaching funding with the Elbagen business competition, and then furthermore we approached and wrote some SBIR grants to basically take the idea further and develop the product. So ultimately what we do is we control mercury pollutants and from the coal-fired power plant flue gas. We have an active research lab at the Wyoming Technology Business Center, and where we can synthetically produce these materials and also test them as we go. And I want to go more into the technology itself here and basically state the problem initially before I go into how we approach it. So on the upper left side, you have a typical power plant, coal-fired power plant generation unit. Ultimately is a burner, if you will, that produces as a side product. A lot of it's a CO2 and a flue gas, but coal contains more than 70 elements out of 96 in a periodic table. So anything that gets vaporized, you also have those elements present in the flue gas. So actually, one could look at it, it's easy to burn the coal, but then with that in mind, you have a lot of pollutants in a really small concentration, believe it or not, that are very challenging to remove. And one of them is, for instance, mercury, which is parts per billion. So as the flue gas exits the plant, it goes through all kinds of control devices, and believe it or not, sometimes those devices take a lot of energy out from the initially generated one. Now, nitrous oxides and sulfur oxides, those were the early, most important pollutants that people controlled. But in the last 10 years, mercury has been a big target, and I believe there's a significant market for this type of technology. And from latest numbers, estimated recurrent control costs for mercury emissions is around $500 million per year in the United States. So it's a very niche market just for one element, but there is a lot of opportunity there, with that said. So how people do control mercury currently? Well, it's an interesting topic because you don't want to reorganize the whole plant to control one single element. So the most convenient way has been injecting this really fine sorbent, if you will. And the idea here is, capturing that high mass transfer between small particles, flue gas, and your residence times are relatively short, so you have to balance those two variables and use perhaps existing devices in place to facilitate this removal. And again, we're technically not capturing mercury, we're just removing it from one phase to the other one, and that's from the gaseous phase into the solid phase. And so the idea here is, again, as your flue gas exits the plant, you inject this fine powder somewhere post-combustion, and then it travels across the duct and gets the powder, picks up the mercury, and then gets captured. Let's say at the baghouse, the powder gets captured. And so you have that mass transfer from a gas phase to the solid phase particles. And all of the mainly market players is activated carbon. This material has been around for thousands of years. It's extremely efficient, but the belief is here that it is expensive. And to increase the efficiency and reduce the costs for capturing mercury, I think there's better solutions for it. And so that's what pollution control technologies try to address here. So I have put in a typical current market division, and you can see 90% of a pie, it's gray colors. So those are all activated carbon companies. And then you have some of the inorganic materials that also have been introduced in the industry. So I'll go more into detail how these materials are divided up. So again, the reference point for capturing mercury from a flue gas would be using activated carbon, where this fine powder gets injected and mercury gets absorbed on a carbon. To produce this material, the technology has been around there, for water purification. So it's a very similar process here as well. You basically pyrolyze initial material, open up the pores, you grind it really fine, and then sometimes you add some activators to really dope the material just specific to oxidize, say, mercury and capture it. It's an expensive process because first of all, you start with a already expensive precursor, and then you have many steps that could also be costly, including the grinding to a really fine size. And then if you look at the mass transfer, yes, you have a carbon particle in a micron size, but the issue here arises when you have a really short residence time. Really what matters is just that instant surface area where mercury gets reacted and captured or picked up from the air or flue gas. Now there's other category in organic sorbents, and so what people have done is found out, okay, there's a very highly reactive mineral to mercury, and we could just use that. And so this is a great concept, and so what you ultimately take a mineral starting material and really finely grind it, and that's all it really is. And again, there's some people that prefer this method because inorganic means that you do not introduce organic, maybe combustible material in your flue gas duct. It has more safety associated with that, and if you have a free mineral or a mine nearby, it could be more efficient as well. Now, what we're focusing is trying to reduce the cost and look at the problem fundamentally, and which is ultimately a mass transfer, what needs to be resolved. And so the idea here is to take a basic material where it's already finely powdered, perhaps grind it even finer, and just coat one single layer, molecular layer around it. And this will produce same effect that carbon-based or inorganic other-based sorbents have. And the idea is that as long as you solve the mass transfer problem, you could address this market and I think create an efficiency. And that's what we are focused on, a very rapid on-site simple activation of a existing byproduct from coal-fired power plants is a fly ash. So if one does that, I believe the cost savings could be tremendous. There could be a savings in transportation costs. A lot of times, say, activated carbon is produced all 2,000 miles away from your current site, and then it has to be shipped in. But if you could just take, say, a small activator, 1% or even less, and just do one single layer molecular activation or coating of the small particles, you could basically create the same effect. and be more efficient. So that's what our company is basically targeted at. We're designing chemicals to coat really fine powders. And again, there's different business models what we're approaching. One could be on an on-site, or one could be a near facility that maybe serves a couple power plants and such. I wanted to give you just a typical early on estimate what we've done based on a preliminary data that we've done in our, now let's see, it's already alpha or beta test that we have conducted. And I think we believe that, for example, we could compete with activated carbon and slash in some instances savings half of the cost, just because the activator is only 1% and it doesn't cost that much to coat a byproduct that's basically free nearby. And so again, some of the benefits we see that this technology could be very versatile. You could have an on-demand, on-site production. The cost savings come from really low material processing costs, and we would also address this issue that some people are worried about fly ash contamination with carbon materials. So it's already an ash, so you would not technically introduce anything else, just recycle it. With tuning the activator properties, we can make temperature resistant. Specifically, a lot of plants, it depends if it's a higher temperature flue gas or lower temperature flue gas. We could design the chemical around that to not have that issue. And also very specific, just targeted at mercury, or recent derivatives of, or material coating, for example, is NOx and SOx resistant. In some instances, this hurts activated carbon. And again, for environmental impacts, this would be a zero-waste material where we would not put out as much expensive material, and it would be just 1-to-1 ratio. The hope is to activator and mercury. So that's in briefly what our company has been working on. I would like to thank our team, and also I haven't included, but definitely without generous funding from NIH that addresses and is concerned about mercury pollution in air, we would not be able to start this project. Our current status is that we have a couple tests lined up this year, beta injection tests. We're actually running one right now here in town. Believe it or not, there's a steam plant that burns coal, so we're injecting our sorbent right there right now, and we've done a lot of testing with other clients. So to upscale it, this is a big challenge because a lot of people are worried about new technologies, especially if you go in a plant that's $1 billion worth plant, injecting a new material. There's always a lot of concerns. If something goes wrong, if it goes offline. So finding testing partners is the biggest challenge right now at this point. But I'm hoping that by spreading the word and being open to technology, new technologies and possibilities, that we can succeed this year and bring this technology to the market. Thank you.
Thank you.
Hi, my name is Poria Nikuyan. I'm one of the co-founders of Resono Pressure Systems. I'd like to acknowledge the help of my colleagues and especially my advisor, that we basically co-founded this company together with the help of Wyoming Technology Business Center, Dr. Benson and Dr. Bowling, which is my direct consultant for this project and this company. I'd like to start my talk with this kind of quote that I see whenever I go to talk with Dr. Bowling in his office. It says that if you can't measure it, it's not real. I have a slightly modified version of that I use, which is if you can't measure it, you cannot improve it. Okay, so let me tell you why I'm saying that. So in any energy conference, any energy community, we are obsessed with using this one term. That before saying that, I just want to submit to you an experiment in order to realize how many times these terms get repeated. If we could just take a shot, a tequila shot, for every time that the term efficiency is repeated in an energy conference, I think we all will understand how many times this term has been used in an energy conference or energy community. So efficiency is important because we have all heard those fantastic numbers that, yeah, if you improve the efficiency of this system or this plant or this machine, it will save a couple of $1 million every year for this plant or for this system, for this company, this aircraft carrier or whatever. But as I think Jason mentioned, that especially in energy and power industry, we have pretty much saturated to the efficiency improvement in many systems, like power plants, like the power cycle. Those have some limitations, and we are very, very close. So nowadays, improvement in efficiency is within a very, very small percentage, okay? 0.1%, 1%, 0.01%. So how this company is related to that, to energy market? We cannot go to, for example, ACE and buy an efficiency meter. You cannot measure efficiency directly. You have to calculate efficiency. And temperature and pressure, usually for power and for thermal efficiency, are those physical quantities that you need to actually measure in order to calculate efficiency. So I'm not going to talk about temperature, but pressure measurement, accurate pressure measurement, can be very difficult. And one of the reasons is that pressure changes with time, and most of the times, especially now at this age of technology, we are really interested with those changes of pressure with time in order to improve our system. Okay. Pressure changes with time. So if you put this term on this change versus time, hertz means how many times it changes in every second, we can go all the way from 0 hertz to hundreds of kilohertz of change in pressure with respect to time. For example, a pressure cooker, that's very, very slow change in pressure buildup of that inside that chamber. An aircraft, whenever you experience a gust, that's in the order of hertz to tens of hertz to 100 hertz of change in pressure around that airplane. A helicopter blade, as it rotates, that's usually in the order of 100 to 1,000 hertz, several kilohertz. And then, for example, for projectiles, we have very, very high rate of change in pressure around that projectile. Okay, so let me just briefly kind of introduce you to how we measure pressure usually. Let's imagine we have a pipe that we want to measure pressure inside this pipe. What we can do is to put a pressure transducer inside that pipe, or we can use a tube and put that pressure measurement system at the end of that pipe, okay? So there are good and bad about each one of these ways that we measure pressure. Usually when you use one single pressure transducer and you put it where you're going to measure, depending on how harsh the environment that you're measuring pressure in is, you may have failure in that pressure sensor. And so you need to buy these more robust pressure transducers, which are way more expensive, and you are still not safe when it comes to vibration, electric shocks, and very, very extreme temperatures. Okay? So the other way, when we use a tube in order to measure pressure, it's very robust because now our sensor is somewhere that is very, very safe. And it's very adaptable because all that we need to do is to cut those tubes and use that sensor for another measurement somewhere else. And a tube usually plays as an isolator between the sensor and where you're going to measure the pressure. So you don't have to be worried about electric shocks or temperature or vibrations. And it's very cost effective because now you can essentially bundle a lot of these pressure transducers together and make one system that has 50 sensors in it, and it's way more cheaper. Yeah, this just as an example, if you want to measure 50 pressures, you need 50 of these single transducers, but if you buy these bundles, you have 50 pressure sensors in one little box, size of a matchbox, and you can just connect it to wherever you want to measure pressure with a tube. Okay, let me give you an example. When in process control and in gas turbine for power generations, these are examples of harsh environments that we have to measure pressure in order to control the process, in order to monitor it and all that stuff. So if vibration, electric shock, and okay, so the picture on the right, on top, I have a sensor that's connected to, for example, a gas turbine combustion chamber. And these are fairly expensive sensors. And if they're selling it to you for $4,000 for each one of these sensors, they're not expecting you to come back in a few years. They're actually expecting you to go back within weeks or months because it's a very, very harsh environment, very high temperatures. So if this sensor fails, we'll have control failure. And when we have control failure, we can have catastrophic system failures. That's why we sometimes use this other approach, that we put the sensor away from where we are going to measure pressure, and then we connect it with a tube, okay? But there are difficulties with that. There is a lack of accuracy when we use this tubing system in order to measure pressure, but I said that it's very important to measure the pressure accurately if you want to improve the efficiency of a system by 0.1%. So what is that problem, okay? Then let's imagine that pipe again, okay, and let's assume that the pressure in that pipe is changing like this sinusoid, okay? I can use this transducer and be very, very accurate. There are very little red dots in here that are my measurements of that actual phenomena. When I put a tube, I start seeing a little bit of lag and amplitude attenuation in that signal. And as I go to longer and longer tube, my measurements become essentially garbage. Like you cannot rely on those measurements. So our solution is that, okay, how do we can solve this problem? Because it's very good to use these tubing systems, but how do we solve for this lack of accuracy? Okay, so I introduced you to these sensors and also the other one. We can only use these sensors for situations where pressure doesn't change that much with time. Very, very small changes with time, in the order of essentially 0 hertz or maybe a couple of hertz. But these other single transducers, you can use them for a very, very wide variety of applications with different frequency changes. Our idea was, okay, if we could somehow extend the use of this tubing system pressure measurement to up to a few kilohertz, we can solve a lot of problems. There are so many applications out there that the range of pressure change in time is within this like 0, maybe 10 to 1 or 2 kilohertz. There are many applications, some real-world applications, engineering applications. We can't go all the way to 100 kilohertz, but if we could just extend the use of this tubing system to kilohertz, 2 kilohertz, we can solve a lot of engineering problems. And we're not creating a new sensor. We're just developing a software with some hardware that goes along with it to enable these accurate measurements that involve a tubing in between wherever you're going to do those measurements and the sensor itself. And we're commercializing this solution. So what are the market segment? Who are the people who are interested? Well, of course, wherever you have an environment that's hard to put sensors in, which is aerospace, is our main target market right now, because in fact, this research was developed for wind and helicopter blade research. And then we have this energy market, which, as I said, is gas turbine, wind energy, all those when we want to measure pressure very accurately, and we don't want to deal with sensor failure. We have also, other than our first target market, which is wind tunnel testing, we have the second one, which is field testing for wind turbines that we're working with Sandia National Lab. So in terms of revenue model, so we have some hardware, some software, some products that we are selling. We also have some customized systems, energy as a service that we can provide to our customers that want to do these kind of measurements. We're done with our proof of concept. We have a system that works. Right now, we're working on a prototype unit, and after figuring out all the bugs, we'll have our first production unit, hopefully in early summer. We already have some potential customers that are very interested in the system and line up. Just yesterday, we got our first energy market kind of customer, which is Purdue Combustion Lab. And we are also partnering with TE Connectivity. I'm not sure if you're familiar, but it's one of the largest manufacturers of pressure sensors. We have a non-disclosure agreement in order to talk about our technology, and they can tell us more about their technology. And we have a strategic partnership with them. Yeah, hopefully we'll see what will happen over the next few months. Thanks a lot.
Great. So we have time for a few questions. What questions do you have of the panelists? Yeah, Mike. Mike, okay.
So could you maybe talk, you can assign the question or take it yourself. So,
okay.
Or if you want to assign it so you can then think about it and then come back and do cleanup, that's good too. We're just kind of wondering if you could talk a little bit about, as you transition from pre-venture through your first growth building phase, what are the capital needs that you have along the way, and how are we meeting those? How are those capital needs being met? Is there any opportunities, insufficiencies in the pipeline capital that kind of models your development process?
So in terms of having money when you're in pre-revenue and you're developing your product or service, the principal way everybody does it is through the Small Business Innovation Research Program. Without that program, there would be a lot fewer technology companies. And this is a phase that nobody wants to pay for. It used to be tech boom days that you could raise money for that. It's hard to raise, it's hard to raise money. It's hard to raise money in Wyoming. But really, if you're in pre-revenue, it's a Small Business Innovation Research Program. The next stage is when they go into initial sales, and investors will like that kind of situation. Private investors tend to be relationship investors. That means that they know the CEO of the company. For you to put money in a company where you don't know the CEO, that's a big deal. And so we will have some. Robert has gotten money from people that he knows. And there's a fund that just started up in Casper, Seed Capital Fund 307 Breakthrough. It was started by the head of CADA, Charles Walsh, and Jared Stack used to be one of our clients with Firehole Technologies. And what they did is they put together a $2 million fund. They got 20 folks to put on to make a commitment for $100,000 apiece. They're just now starting to try to identify companies. They want to make investments of $75,000 to $200,000. They've developed a relationship with 5 different other seed capital funds throughout the state. So if you're in a seed capital fund, you're looking for deal flow. And so this would allow them to put money in and then take something there. Mike, for the most part, our clients bootstrap it. And bootstrapping is through your own assets and getting cash flow going as quickly as possible. So a lot of them, it's the word is don't quit the day job too soon. What we need to do is get some action going here, to develop some money and coming in, and then eventually you can quit the day job. It takes longer, but a lot of times that's the only way they can do the company, because they don't know any wealthy people, and there's no way that other people are going to put money into their companies. When I first came here 12 years ago, in terms of the lack of capital that was here, I didn't really feel like we had deals that investors would really be interested in, but I do now. And I'm really pleased that, so the Casper thing in other communities, everybody's talking about it up in Sheridan. When they raise, and I think it will stimulate more. So I know that these guys went to 20 people, and I tell you, it was a lot easier raising than they thought it would be. And then I'm talking to people up in Casper, and I ask, are you a member of it? He says, no, they didn't come ask me. They were like insulted that they weren't asked to be a part of this fund. So I think if we can kind of get it going, we can do some more stuff around capital, which we need. Make it easier to do these businesses faster. Great question. Other questions? Yeah, Tim.
Robert, this morning we talked about composite materials and natural gas usage. Have you thought about cooperating with somebody that's using composite materials for the building of your turbine wings?
Yeah, I mean, we don't really care about the material right now. It's actually the geometry that makes it much better. And actually, we just don't have the resources right now to compare different materials against each other. So we'd love to look at composites, but it's just a resource question. We need more money.
Mark.
I was fascinated with the conversation about variability of supply, but yes, yeah. And so I actually am also curious about the variability of demand, as everybody's going to variable speed motors and different types of efficiency improvements and smart grid, et cetera. Does that problem compound itself?
Sure. Is this? Yeah, this is on. So the way renewables right now are categorized, they're actually categorized as a load. So if you talk to a dispatcher, there might be one in the room actually, dispatcher looks at their historical variability as a function of renewables and as load. And so you see a lot of things like arc furnaces and these highly nonlinear electronic devices going onto the system in spades. I mean, especially here in the Rocky Mountain region, we have some really strange dynamics that end up being on the system from the load side. And what this does actually is it doesn't really care about the source of the disturbance, because what it's doing is it's measuring disturbance effectively, or variability, and it's acting to cancel that out. Those are the dorky slides I skipped over. But that's what it's doing. It's effectively it's attempting to cancel those variabilities out from the load side as well as the demand side. Now it's compounded, as you suggested, these new types of loads. Again, these kind of new highly nonlinear loads. But in general, yes, there's a strange effect, the interaction between load and generation that's variable. Now, if you're familiar with this trend, they call it the duck trend, where you have this inversion of power in the middle of the day. So you actually have to ramp units down in the middle of the day because you have highest variability or highest output from photovoltaics. But in the Southwest, for example, where you have monsoons roll in, you'll have this really strange interaction between load and generation, where you have a ramping down of photovoltaics and a ramping up of people going home and turning their stuff on. And so it actually has this bizarre balance effect where you see high frequency deviations in there occasionally. And that's all load based. It's a load following problem. And so what a smart control system does is it looks at all of those factors. It factors in everything and uses what resources it has available to it, say large storage devices, and tries to make the best of a kind of a bad situation where you have a bad interaction between highly variable load and generation. Does that help much?
Absolutely.
Outstanding.
Other questions for the panelists? Yeah,
I've got
Richard.
a general question.
Sure.
One of my observations and one of my concerns is the state or people in the state are investing considerable sums of money and their own personal time and resources. And one of the things we have to be concerned about is that the stickiness that they stay in the state, they don't move elsewhere to set their businesses up. And I'm interested to hear from each of our panelists about how they see some of the challenges about creating this stickiness by getting engagement both with industry and also some of the challenges that you're facing as you see your growth vision for your companies and staying in Wyoming.
So Richard, your question is, how do they see themselves? What is there about the situation that would keep them in Wyoming?
That's right.
Yeah,
I'll take the first stab at it.
yeah.
I'll take a stab at it. I love the state. Think it's a great place. Like to fish, hunt, do things like that. But ultimately, the initial question about money, where the money takes you, I guess is a big part of where you end up. Can't make money here, can't stay here. So I think the tax environment and things like that in the state are favorable to a company like mine, where I'm trying to get capital initially, which I've been able to successfully do a little bit. And then the growth part of it seems less constrained than most other places that I've investigated. The Rocky Mountain region is, in my case, particularly inflexible or conservative as it relates to power because it's a regulated monopoly, as everybody knows. And so it's they don't have as much freedom as a place. Say like Duke, I was kind of dumping on them earlier, giving them a hard time about their system. But they actually have a team of renewable generation folks who focus their 9 to 5 on trying to do renewable integration. So from that perspective, it might be better to move to the East Coast. Other than that, and I guess in the Pacific Southwest, other than that, it's a very favorable environment for a guy like myself.
Hello. Okay, works. I would probably say that, well, in words of really famous CEO, it was just recently I heard that, you know, you do not want to go to Silicon Valley. You're gonna basically go broke just by living there. So I think Wyoming's actually opposite of it. As a startup business, you could probably get all the benefits to live here and to have your startup in a state that actually supports it, and you get a lot of perhaps, you know, sponsored funding, technology business centers that are open. There's not that much competition, and but again, it depends on the growth of your business. If you need those customers and you need to see them on daily basis, obviously you need to be in larger areas. But I do think technology helps. There's a lot of communication, especially. It doesn't matter where the research lab is. You know, it could be in the middle of nowhere. If you do have people there that work, you could get around it, and you know, connecting with the clients and traveling is always an option. So I think Wyoming has its benefits to be here, and especially for a really, you know, young startups. Once you grow, obviously you need larger cities and hubs, you know, in a better locations. But initially, I think Wyoming's a pretty good place to be. So hopefully that answers.
Yeah, go ahead, Boy.
Okay. My answer to that question is that for a startup, for a technology company, the most valuable asset is the people that you can hire and you can work with. I believe that University of Wyoming, especially the engineering college, actually is very underrated. We are graduating very, very smart people. I mean, these guys are some of the smartest people that I've ever met in my life. And no, I'm serious. And when I want to hire somebody, I much rather hire someone that I know, that I worked with as a grad student, as an undergrad. So I think the most valuable asset is that the fact that I'm a graduate student at University of Wyoming. I know a lot of people there. It will be very easy for me to recruit for the company. And so I would say my political view would be just don't cut funding on the university, because it's it's a big hope for technology advancement and entrepreneurship for the state of Wyoming, because if we don't graduate good students, or if we graduate good students and we don't have this kind of relationship between startups and graduates, they're going to leave. And so, yeah, I think Wyoming is very good for me because I know the university, I know the community that is involved with the type of research that I'm doing for my company.
Right, Robert.
Yeah, we love it here. We like the wind. We like the no state income tax. As an entrepreneur, you have to conserve cash, and you're able to do more here with less money. I think, though, going forward, our biggest challenge is going to be recruiting other people here. Like, if we need a specialized skill, it's going to be very difficult for us to bring a PhD student from Raleigh, North Carolina to Laramie, Wyoming. And I think that's our biggest downside going forward. So I reiterate what they say, but attracting new people is difficult.
Great question, Richard. We've run out of time for questions. These folks will be here for a while. So if you have questions following this, come on up and talk to them. And will you please now join me in thanking the panel for great